So from today onwards we will start the sixth module, synchronous motor drives. So the basic topics included in this module: the synchronous motor drive, and introduction to V/F control in synchronous motors, permanent magnet synchronous motor drive. PMSM stands for the permanent magnet synchronous motor drive. And what are the different types? What are the control requirements? Different converter circuits and modes of operation. And the last topic is the microcontroller based permanent magnet synchronous motor drive. And in the syllabus it is clearly written that schematic only required. So if you see, this is syllabus of the last module. So if you see, it's all about the permanent magnet synchronous machine drive and its different types, the control requirements, the converter circuits, and the modes of operation. And the initial part, the basic part, include the synchronous motor drives, its introduction to the V/F control. Okay, so in this video lecture I will be covering the basic concept about the synchronous motor drive. Its variable frequency operation, what are the different types of modes, etc. Okay, so we'll start with the basic working of a synchronous machine. So all of you know that the synchronous machine working, we will be giving a three-phase AC supply to the stator. So the stator will produce a rotating magnetic field rotating at the synchronous frequency, and this is the rotor of the machine. The rotor will be excited with a DC supply, or you can use a permanent magnet instead of that. When the rotor field winding is excited with this DC supply, it will act as an electromagnet. So the rotor creates rotor poles. Due to the stator three-phase supply, a rotating magnetic field is produced, which also produces a stator poles. So there are two fields. One is the stator DC field, another is a revolving. One is the rotor DC field, another is a stator revolving magnetic field. Due to the interaction of these two fields, the torque is produced. Okay, and the working of the synchronous motor is such that these two fields are always in synchronism. So this synchronous motor is always said to be a constant speed motor. If you do a sudden loading to this machine, what happens is that there are chances the rotor may fall out of synchronism, so that in that case the machine may lose its stability. So this is the basic working of a synchronous motor. Our aim is to control the speed of this induction machine using some power electronic devices. So the machine stator, and this is the rotor of the machine. The stator is fed from three-phase AC supply with a definite voltage and a frequency. So the speed of the induction machine, N of the induction machine, can be controlled by varying supply frequency or the source frequency, because Ns, the synchronous speed, is equal to 120 F by P. So if you vary the frequency of the source, the synchronous speed varies. Synchronous speed varies means the rotating magnetic field speed varies. That is actually determining the speed of the rotor. Okay, but in earlier the problem was that there were no frequency varying sources. So here is a source, a three-phase source. You have to vary the frequency of the source, but conventionally it was very difficult to vary the frequency of the source. But nowadays, with the advancement in power electronic technology due to semiconductor advancement, it is possible that with the help of a VSI here or a cycloconverter, power electronic devices, you can easily vary the frequency of the source. Thus you can easily vary or easily control the speed of synchronous motor. And There are different types of synchronous motors available. Already you will be knowing this. The first one being called the wound rotor type. The second type of synchronous motor is called the permanent magnet synchronous motor. The third type generally synchronous reluctance and hysteresis motors, etc. These are the varieties of synchronous motor available. So what is wound rotor type? So wound rotor type, I have already said that the stator is excited with a three-phase supply, AC supply. The rotor field winding is given with a DC source. So this field winding is connected to this DC source and it will act as an electromagnet here. So this is actually the wound rotor type. But what is a permanent magnet synchronous machine? In permanent magnet synchronous machine, this is the arrangement. This figure we can explain using this figure. The stator is supplied with the AC source as in the case of wound rotor, but instead of this using a DC separate supply and making it as a magnet, we will be using a permanent magnet at the rotor side. Okay, the rotor is a permanent magnet. So what is the advantage we are getting? The DC field, DC source, the slip ring brushes and the DC losses, the field winding losses that can be produced in this wound rotor type machine, we can eliminate here in the permanent magnet drive machine. So these are the advantages of permanent magnet. So I am just explaining the basics about synchronous machine. Another thing, the fundamental thing that is happening in a synchronous machine is that you must learn about what is the meaning of pull out torque in a synchronous machine, or sometimes it is called the steady state stability limit. What is the meaning of steady state stability limit of a synchronous machine, or what is the pull out torque of a synchronous machine? So if you take this as a synchronous machine and assume that this is a per phase stator voltage given, okay, and this is the rotor, this is the battery EMF for the DC voltage connected to this rotor is E. Assume that it is like that, okay, field excitation voltage. Then the power developed by the synchronous motor is equal to PM is equal to 3 into V into this E divided by the reactance, synchronous reactance Xs into angle between this V and T, sine delta. Okay, now what is torque? Torque is equal to power by omega S. Okay, so 3V into E by Xs into omega S into sine delta. And we know that for a given frequency, T will be maximum when delta is equal to 90 degree. When you substitute delta is equal to 90 in this equation, you will get torque maximum is equal to 3V into E divided by Xs into omega S. So this term, and after which what happens, this is the maximum torque that can be produced in a synchronous machine, and this is known as the pull out torque or the steady state stability limit. And if you exceed this value, what is going to happen is that the machine may lose out of synchronism. These two, the two magnetic field may fall out of lock, and the machine may lose its synchronism. So this term is very important, the pull out torque. Now we will just study the basics. The intro part is the V by F control basics in a synchronous motor drive. This is similar to induction motor drive also, but again we will study it. The variable frequency, control of synchronous motor. So again, just for understanding it, let me draw the circuit once again. This is the stator is fed with a three-phase supply with a definite frequency and voltage. and rotor is either permanent magnet or you can supply using a DC source C. And we know that to control the speed of a synchronous machine, we can control frequency. Why? Because ns equal to 120 f by p. So if you vary frequency, ns varies. Ns varies means the rotating magnetic field here, its speed changes. That is actually the rotor speed. Okay, so you can control speed by changing the frequency. But when you change the frequency, it is similar to induction motor drive, because until the base speed, assume that this is the base speed of the machine or the rated speed of the machine. When you control frequency, you have to control V also, so that this V by F ratio should be maintained constant until the base speed. So the frequency control you will be doing in such a way that when you control the frequency, you have to control V also, so that V by F ratio should be maintained constant for the constant flux operation. So until base speed, this is the frequency control. So after base speed, what is going to happen is that you cannot do this V by F control, because if the after base speed, if you increase this V, it will be more than the rated value. So after base speed, we will be using V constant and we will be controlling F only. Okay, so this is basically the V by F operation in synchronous machine. This is similar to induction motor drive. Until the base speed, we will be using V by F control, and after that we will be using this V constant. Okay, and this V by F control or this variable frequency control in synchronous motor, synchronous motors operate in two different modes generally, basically. So we will study that two different modes. The first mode is called true synchronous mode, or it is known as the open loop mode. There is no closed loop operation. Another mode is known as the self-controlled mode. So variable frequency control in synchronous machine, synchronous motors operate variable frequency control in synchronous machine, which is operating in two different modes. So first mode is true synchronous speed mode, and the second mode is the self-controlled mode. So today in this video, lecture, we will be seeing the true synchronous mode of operation, or the open loop mode of operation. So in the open loop mode of this operation, what the basic idea is that we will give a frequency, desired frequency command to this synchronous motor controlled VSI, and this control is given by providing a delay circuit. Why this delay circuit? Means that when the frequency changes, the rotor also should be able to catch up. Okay, if you suddenly changes this frequency, the rotor may not be able to catch up, machine may fall out of synchronism. So first of all, let me draw the block diagram of this. You have a synchronous motor. It's fed by a DC. The stator of this machine should be supplied with a variable frequency and voltage source. So this source we can use a VSI to feed that stator. But VSI is an inverter. Its input must be DC, output is AC. Okay. So assume that our available source was AC. So this is three-phase AC. So using a controlled rectifier, we will be converting into DC. Okay. So the controlled rectifier output is given to the VSI using an inductive capacitor filter. This is just a schematic I am drawing. So this is AC supply. Output of the rectifier is DC. This is a filtered DC, constant DC. This is given to VSI. VSI output is AC with the desired voltage and frequency given to synchronous motor. Okay. Now the open loop control is like this. You will be giving the desired frequency command for the desired frequency for desired speed, and it is given to this VSI by providing a delay circuit. This block is known as the delay circuit. Why the delay? So that the rotor speed is able to track the changes in frequency. If you given all of a sudden, the rotor may not be able to catch up. That is the reason why you are using a delay circuit, and this frequency is given to the VSI, so that the VSI switches can be turned on and turned on based on this frequency. Okay, so this frequency is again given to we have seen in induction motor drive also, this circuit is given to a flux control block. This flux control block produces a reference voltage V star. Okay, so based on that V star, we can give pulse. Firing circuit block is there. Based on this V star, different firing angle can be produced. So the operation is very simple. This is actually the V by F control. So frequency is controlled here. At the same time, if we are using below base speed operation, we have to control V also. So this is the block for that. V is also adjusted. And above base speed, if you control frequency, the thing is you will be only controlling the frequency. Voltage has to remain constant. Okay, so this controlled rectifier pulses, based on that we can control this DC voltage by controlling these firing pulses here. So the firing pulse can be controlled by generating a reference voltage based on this V by F operation. Okay, so this is actually the true synchronous mode of operation. In this true synchronous mode, the stator frequency, supply frequency is controlled from an independent source. Here, the frequency from its initial to this desired value is changed gradually, so that the difference between synchronous speed and the rotor speed is always small. And this allows rotor speed to track the changes in synchronous speed. Okay, and when the desired synchronous speed is reached, the rotor pulls into step. And this is what is happening in this drive. Okay, and this scheme is commonly used. If you can read the textbook, it is clearly written that it is commonly used for the control of multiple synchronous or permanent magnet motor, textile, paper mills, etc. Where you require the accurate speed tracking between motors is required. So this is generally the block diagram. The feature is that F must be changed gradually, so that the rotor may be able to follow this.